Thank you. First, of course, I would like to thank the organizer of this wonderful program and of this excellent conference. I think it's very timely, really, in the sense that this field really matured, right? Okay, so I will continue this line that was started by Sharon and then continued by Chad. That what a remarkable 25, 30 years it's been. So from this 1990s pictures of, let's be frank, mass, right, to this wonderful, it was a mass, yes, but it was very inspirational mass. It basically it was inspirational mass. And to where we are now. So I will not show all these wonderful pictures of the structures because you've already seen them. So it's breathtaking. Partially, this whole progress in self-assembly that we witnessed can be attributed to the quality of building blocks. So our ability to get this excellent building blocks. This includes the games we can play with particle shape, size, valence, and what I would call color by putting this DNA on top of these particles. And you've seen how this all played, how many structures can be formed. What I want to emphasize is that even though the zoo of building blocks now is huge, and in principle, when we are talking about DNA decorated particles, it's virtually unlimited. In each individual example, in each individual experiment, we normally employ only small alphabet or small subset of this zoo. We play with 2, 1, sometimes maybe 3 particles at once. So, in principle, this ability to have such a variability of building blocks tells us that, oh, what a wonderful world it would be if we could put together tens of those types. That certainly should increase our ability of designing stuff, right? But yeah. I don't have the term for it. I just make this claim. I had the term. I would call it complexity catastrophe. But after sausage catastrophe, I think I need to rebrand somehow into something gastronomical. But the point is, when you put lots of stuff together, we don't need to do much of computation to predict, to tell our experimental colleagues what will come out of it. It will be mass, right? So the thing, even though our ability to design things probably increases when we are interested in ground state, what also is increasing is ability of this thing go sideways, ability of the thing to get trapped in some metastable state. So what to do about this? Well, one solution that I came up with a while ago was to take best features of each. So we already discussed these particles in different contexts. I don't have unified name for it. Here I call them designer particles. Occasionally I call them polychromatic patchy particles. So basically, what you see on the left is how I saw about them like 10 years ago. So I literally copy and pasted from old talk. This is more or less how you can think of them for some simulation, right? It's a patchy particle where each individual patch is addressable, and this is how the schematics of how these particles actually implemented by my experimental colleagues. Specifically, I took this from the recent paper of Oleg Gang's group. So you see my overall optimism about this community. So whereas Sharon was hesitant of imagining this thing being available anytime soon, I never doubted my experimental colleagues. So when I started to play with this, of course it was not available. Yeah, you do. You do. Yes. Okay, we're all over-optimistic, that's true, but it works, see? So at the end of the day, it works. Several things, side comments. So in this field, right, since so many new things pop up, you need to name this each time. So branding is a big thing. So we are almost like this, you know, people in the age of exploration. You can name things. The problem is that not all names will stick. So that's why, I mean, I'm a little bit hesitant about how should things be called. The second thing, of course, is when it comes to convincing your experimental colleagues to do something, the best inspiration for me was this movie Inception, right? Where you don't really tell them what to do. You make it sound so that this idea somehow propagates deep enough and then it resurfaces. So that's basically what I'm doing here, okay? So anyway, so in order to demonstrate just how using of these designer particles or polychromatic particles helps, we had some generic fundamental argument why they should work, but then of course nothing works better than some movie. So we it's been already 10 years when we constructed what we thought was Empire State Building model. So I normally would run the movie, but it's not PG-13, so I stopped doing this. Anyway, so the amazing, there are several amazing things about this system. So first of all, each of these statues contains 200 plus particles, right? Out of which the number of particle types is like 70, 78, whatever. Now, it goes into this configuration pretty much without ever sticking to any undesired metastable state, right to ground state. I will tell a little bit more about why and how, but this was just a conceptual show that this thing works. You can put tons of particles of different types, and they will assemble what you want. So then, of course, again, my wonderful experimental colleagues did this proof of principle experiment. So what we designed together there is what we thought is Vitruvian man, right? So nano-Vitruvian man, but now I look back, it's more like Minecraft character, right? So yeah, probably better analogy. But anyway, you know, scientists always think of something beautiful, and then what comes out is like not always, but something that works. Okay. Anyway, so back then, in this case, you can see there are 5 different elements that don't necessarily build this this structure that we want with 100% yield, but yield is decent. So you can see it here and there. Now, of course, it's been miles away from our dream of this Empire State Building, but now. Why I go back to this story is because now finally the field matured. So it's now a time when you could put many things at once. You can design those building blocks properly. You can make many of them. You can mix and match. All you need now, this is the time for us theorists to come in and say, okay, try this, because yes, you can do all of this, but this is expensive experiment. So you can literally order each of these individual DNA, and it's sort of becomes high responsibility, because if this doesn't work, it's so much, you know, taxpayers' money paid for nothing. Anyway, so this is the moment where I should go back to this Empire State Building and open some secrets how it actually works. So there was this, I call them principles, but these are really tricks, right? So what we figured out is that you need to do several things. First, you need to be very forceful about deciding how things should nucleate. Classically, you rely on nucleation to occur somehow, right? Here, because we have all this control, we can decide what part of your system will work as your nucleation center. So in this particular case, and in fact in the case of Empire State Building itself, we had this two-stage process. So we first self-assembled the core that will dictate the overall size of the system. So what you see here is Empire State Building, how it would look if it were built in 1970s, right? So I guess low point of Walls architecture, at least in my book. Yeah, so you can see this box. This box 3 by 3 by 7. So the question is how you make it 7, not 8 or 9, right? So yeah, you do it brute force. You first build a seed, which itself is one-dimensional string. Each particle there have its own color. So that's how you can control its length. But then, interestingly, to decorate it and make it into a box, you really can reuse the same colors many times. So as a result, the actual cost of production here is 7 particles to make this core and then 6 more particles to decorate. So if I needed to add a couple more layers, all I needed just to elongate this core, right? So then the second, so this is my second trick. I use the symmetry of this thing and any element of repetitive, any repeating motif, which is not the same thing as symmetry, of course, right? So when you see that you can use the same blocks again elsewhere, you use it. And then finally, that's something that was not really utilized in that experiment that I've shown you. That is use of what I call cooperative binding. What really I mean is the following, that each new particle that comes there, except of this first, this seed and the first generation, which are strongly attracted to this seed, all other particles, they come and sit there connecting to more than one particle. So you play with the strength of this attraction in such a way that just a single contact is not enough. In this way, when the particle comes and sits and it's free energy-wise preferred state for that particle, it also means that it occupies its correct seat. So that's what I call robust growth. So in other words, you don't need multi-particle moves in order to correct errors. If the particle is sitting in the wrong place, it will depart. If it has enough contacts, it is a correct place for it to be. That's how you basically, all your growth becomes simply diffusion limited. You don't need any extra rearrangements to correct errors there. Then we did the same thing for crystal, which is sort of, in a sense, going back to something simpler, because of course controlling the overall shape is harder than controlling the crystalline structure. So what this example means to show is that you can design and color this polychromatic patchy particles in a way that a single rewiring here allows you to switch between the cubic and hexagonal diamond. So for one case it grows cubic diamond, for another case it grows hexagonal diamond. So this is a result of simulation, and in fact this is the case when, again, the growth is completely diffusion limited. So you don't need any rearrangement. That is certainly an excessive number of particles to grow the diamond, right? So we had eight particle types, but it was chosen to make this growth robust, as I said. If I just remove this constraint that it should robustly grow, I could go to a smaller number. But again, kinetic control occasionally is more important than the control over ground state. So at this point, let us have a bigger view of what we're actually doing. So now that I hope I convince you that you can push the envelope a little bit further to mix and match many particle types and architectures, we find ourselves not so much in the world of new chemistry, but rather in the world of new biology. It's really a biological world where we have so many different chemicals playing together. So the complexity now doesn't emerge from originally simple building blocks. Rather, we encode complexity by a complexity of the pool of building blocks that we feed it in. So in that sense, the self-assembly can be viewed as an information processing process. Information processing. We input information in the form of building blocks, and the output is some complex structure. So these are examples, biological inspirations for what tricks we can use. So many of them we already use. So how you can make what I call informational matter. So in other words, the matter that contains lots of information down there. So one method is folding, right? It's when you design sequence and then the sequence gives you some three-dimensional arrangement. We already use it, I mean, its community use it heavily in the form of DNA nanotechnology. So DNA origami is booming field, and I would say that we understand folding of DNA. Until recently, we understood folding of DNA may be better than folding of proteins. Now, with emergence of AlphaFold and advanced machine learning, probably proteins will catch up. So at some point, we will be able to design proteins with desired pairwise interaction, shape, and things like that, a function. Another method, of course, is self-assembly that we discussed. So self-assembly, of course, is omnipresent in biology, but we are all in self-assembly. And the third one is what I call templating, right? So example of templating is now famous PCR reaction, when you have a single strand of DNA and then you copy it onto another one with the help of special enzymes. Okay, so now that we have this vision of this information processing from input in the form of building blocks to the output in the form of structure, it's the right time to ask a question: what exactly complexity is? So when it comes to input, that is relatively easy. We can assign some information entropy to pretty much any pool of building blocks or to the sequence of certain polymer. But what exactly is complexity of a structure? So here is my attempt to answer this question. So you can ask, of course, people ask this question many times in various contexts. What is the complexity of these bit strings? So can you tell me which one looks more complex? Number 1, number 2, number 3? Which one is more complex? Yeah, number 3 seems to be more complex, and in a funny way, on zeroth level, you say, oh, wait a moment, these are all strings of given lengths which have absolutely identical probability of emergence, right? So there is no real reason why one is better than the other. But then, of course, the trick is you look at the very long string and you use it as an ensemble to see what different how similar are different substrings. If you look at certain substrings, how well you can predict the string beyond those substrings. So that's where this notion of Shannon information entropy comes from. So you essentially assign block entropy to substring of certain lengths. So you take a substring of certain lengths, and then you ask yourself how many of these substrings you actually have in your system. So that's how you define the block entropy, and then you can, of course, compute the entropy per character. So if you have now long text, then in principle, that's how you can determine how much a single letter in Shakespeare book, how much information it encodes. So you just take the limit of very long block and divide by this length of this block. This limit kind of exists. It's non-trivial actually to compute. Same tricks, of course, are done in bioinformatics and in other places. So there are alternative definitions of complexity, and mathematicians all the time show which one is stronger, which one is weaker, which one is subset of the other, but that's not terribly important for us now. Let's just enumerate several. So there is Kolmogorov complexity. Basically, you write a program that generates that pattern that you observe, and you ask how long that program is. So if that program is really primitive, then probably it's easy to encode. If it's long, then yeah, it's more complex. Then somewhat related is Lamper-Zeev complexity. This is essentially the compression scheme that is still being used in pretty much all the files that you compress, right? So you essentially the Pullman versions of measure of complexity are the following: you take a picture and then you compress it, and then you ask, okay, so how big my file is? Of course, then the question is whether it's lossless or not compression. So what I'm referring to here is lossless compression, which means then the analog of PNG or GIF, something like that, but not JPEG, right? JPEG has some pre-existing information about the content. Okay, so now let us apply some of this idea to material objects. So let us consider this case of square blocks which can be put together into this structure here. You can, in principle, start applying the ideas from information theory here. We need to identify what is the word is. A word here will be in my treatment will be the following. I will start at a certain point, and I will make several steps from it. So basically, I represent my structure as a spatial graph. Each point here has some number of nearest neighbors, and then second nearest neighbors, blah, blah, blah. So then I can ask how many types of the clusters, when I only look at the nearest neighbors, how many types of clusters for the so this k stands how far I went from my origin. So k equals 1 means I only take my nearest neighbor. So I can ask how many k clusters are there. So in this case, for k equals 1, 2, I have 2 of this, 1 of this, 2 of this. So I can, in principle, now start computing the information entropy content of this block entropy in Shannon style as before. So here is what I get if I apply this to these three structures. These are three obvious examples. One is periodic structure, another is DLA, just random mass, seemingly. And second is very well structured Eiffel Tower. So not terribly surprising. When I start computing information entropy of this structure per block, here is what I get. So it's cluster information entropy per in bits here. So you can see that, of course, the periodic structure becomes at some point boring, so there is no new information appearing beyond certain size of the cluster. The Eiffel Tower is more interesting, but then, of course, this random aggregate, the DLA aggregate, had lots of information entropy in it. But we all know, right, this information entropy is kind of silly. We know that in order to generate a DLA cluster, you don't need much of control. It's because many of those configurations in random state are equally useless for us, right? So we shouldn't really assign them or treat them as something as a meaningful measure of complexity. So how to escape this paradox? So when you just apply the Shannon entropy dumbly, what you get is the random thing will have maximum information content, which is very counterintuitive. It's not really what we call information content. So the escape is like this. So if you already know all your composition of clusters are different size, you can then ask the following question. Suppose I want to determine, so in this case I have a cluster of depths of order 3, right? And I can decompose it into subclusters of depth 2. Right, so it consists of this cluster consists of this subcluster, then this subcluster, etc. So it consists of these four different subclusters of lower order. Now, if I generate this bigger cluster in completely Markovian way, then I have certain expectation about how many of these subclusters, of these clusters of order 3 I will have. It will be the number of clusters, number of such cores, times the probability of making this right move, this left move, down move, and up move. Up in this case is empty. So I can make this naive estimate and then compare this to actual number of such clusters in my structure. So that will basically mean how much non-trivial information is there on given length scale. So when I make this construction, what occurs is very interesting. So first of all, that measure, this information increment measure, naturally becomes 0 for 2D lattice starting with the size of the unit cell. It is very small for the case of DLA. I cannot really compute it beyond second order. At that point, all clusters become unique there, so it's no longer meaningful, a meaningful number. But it keeps increasing for the case of this Eiffel Tower. So there is some non-trivial arrangement still occurring. So non-trivial structure still occurring at the scale of this bigger clusters in that case. So it sort of captures our understanding of complexity between these three pictures. So I think I'm running already close to the end, so that's why I have this sort of big chunk of my talk, which was more about evolution and origin of life. Luckily, it's quite detached from the rest of the topic. That's why I will just skip it and go to the end. So just believe me, I mean, there is some interesting sub-talk about the origin of life. If you want to know more, I will tell you. It's here. Okay, this is. Did you figure it out or not? Yeah, more or less, we did. I did. So again, this is joint work with my colleague Sergei Maslov. Here we are doing our work, I guess. So this is basically, yeah. So yeah, this is the talk. Goes, it plays great. So. So now I'll skip to the end. So what I meant to say is the following. The connection between this evolutionary part, which I didn't show, and the complexity part that I did show. We all discussed here, of course, how to convert our wonderful structure into something useful, right? So to make it functional. And normally the way how we think, okay, we are mostly control freaks here, right? So in the sense that we want to design a particular arrangement of particles so that they would do a particular function that we have in mind. But really, maybe on a big scale, that's not the optimal way of approaching any engineering at all. I use this term intelligent design, which in this country, those of you who come from abroad might not be familiar with this terminology, but in this country, everyone who doesn't like evolution and doesn't want to sound like very religious, etc., they say intelligent design is an alternative to evolution. Then the argument, of course, is that there is a God who designed everything, and that can't you see this? So this is a wonderful term, by the way. I mean, we should have owned it, right? So when we say when we say rational design, I don't know, intelligent design is better. But anyway, so what I came to understand is that maybe intelligent design is really a stupid way of designing things. Maybe evolution by itself is a better way of engineering stuff. Let me give you a simple example. We are all living through this AI revolution now. Now, what scares us about AI is that we kind of understand the basic principles which are put there, but we are scared but what comes out of it, because we cannot really understand what's happening in that black box, right? So somehow it feels like it thinks itself. It feels like it finds a solution by itself. You don't know what's happening. It's almost like I now have grown-up kids and I understand this feeling, right? So they actually function their way. They somehow create something and you cannot understand how it comes out to be. Maybe that is actually a smarter or wiser way of designing things. So now what I'm saying is the following. Maybe our strong position in this field is that we are arguably in the best, have all the tools to employ evolution technologies or evolution approaches in achieving particular functions. So here comes inception part, right? Don't judge me harsh for my art, right? So we have this DNA code of a structure, right? So we literally have it. We have some DNA which tell our structures what to do and how to respond to particular stimulus. So you can imagine that you have this platform where for particular input of chemical input or optical input, you will get particular output, right? This one, again, don't judge me harsh. Okay, this output. If I like this output, I might keep this code, but if I don't like, I might want to modify it. So you can imagine a situation when you have this code which is being mutated one way or another. And then you can decide whether what you like you will keep or not. So you can imagine the high throughput experiment where you have multiple of those codes. Some of them perform better, you select them, then you modify it, and then you optimize it, but you optimize it by actually simulated evolution. So in a sense, I'm killing my profession because theories there are almost unnecessary. Instead of going to make a model and telling our experimental colleagues what is the best way of achieving particular functionality, they will just go through this protocol and they will optimize the structure or they will find the structure that will perform particular job. But okay, by that time I probably will be deep in retirement, so it's okay, I guess. So anyway, so let me leave you with this concept. Thank you.
Are there questions? Yes. Actually, I have just a comment. Don't be so optimistic about your retirement age from the point of view. You don't need to wait necessarily so long for this to be realized experimentally.
Okay. Yeah, that's okay. Yeah, I take my words back. Yes, I'm still very optimistic about my colleagues. So yes.
So my first question is, in the minimal model, can I just use my alphabets? Okay. So your model for the Empire State Building, was that a minimal model?
Oh, define minimal.
Meaning, did you figure out that the minimum
number of blocks?
Number of, like, you needed 13 different kinds of particles? And
It's as I said, my biggest constraint was always to avoid kinetic traps. So obviously I could do better if I only cared about this being ground state. I could decrease number of building blocks.
You did it by trial and error, right? Or I'm trying to ask, like, have you figured out a way to take a target structure and then figure out somehow, based on some measure of the complexity, which still eludes me, what is the minimal number of building blocks that one would need? Like Michael Brenner is.
We keep discussing this, right? So, and it is a meaningful question to ask, which I didn't go to exactly because I really cared a lot about the kinetics. So that's why we wanted to. So we had these tricks. We tried to be as minimal as possible. I cannot mathematically prove that it's minimal. So we had this a set of rules how to locally minimize how to remove redundancies. So we knew which two particles could become identical without sacrificing the self-assembly process. So we locally, you could say, we found some local minimum. Whether it's global or not, it's a matter of complicated discussion, primarily because we really wanted, our constraint was not to preserve the ground state. Our constraint was to preserve the kinetic, this 100% yield, right? So yes, it's a formidable problem, but
here's what I think is tricky about connecting it to complexity. So, like, we might self-assemble some structures, like the one I showed with 432 particles in the unit cell. And you might do the simulation, and every single time you get the same structure. Then we take a different structure with, I don't know, 100 particles in the unit cell.
Yes.
One might say that one's less complex. I don't know.
Yes.
And then, but there's could be all kinds of competing polymorphs.
Yes.
Right. And so, how do you then?
Yes. Okay. I see what you mean. There is sort of a empirical observation that there is a value of reducing the alphabet. Oleg can talk more about this. So if you have a choice of whether to use minimal or not minimal model, in experiment, normally minimal works better because of kinetic traps. I am not entirely sure that this is sort of law of nature, because my gut feeling is that it probably requires better choice of conditions
but a minimal model might give you the structure you want, but only 2 out of every 10 times. Then if you could tweak the model, add a little negative design piece so that you always get what you want, but then it's more complicated than the original minimal model.
It will be, yeah. So yeah, so yeah. No. What I said is something different. What I said is that imagine that you know that you have a minimal model and then not this model with extra constraints. So it is not entirely clear which one will assemble better.
For sure.
Right, so empirically, experimentally, it looks like minimal assembles better. right? But I don't think this is I cannot make a claim that this is fundamental law. It's probably not. It's probably not. Exactly. So it's much more nuanced than that. I don't have a good answer there.
Thanks.
Yes.
Grant.
So I'm sure you know this work, but Don Frankel and Will Jacobs have all of this nice work on addressable self-assembly and avoiding kinetic traps. And one of the things that they point out is that you really need a basically mutually exclusive set of interactions. So there can't be weak, non-specific interactions. And it wasn't clear to me if that's the case that you.
Yeah, that's more or less yeah.
So if you were to add, as physical systems typically have, right, some sort of weaker interactions. That are favorable,
welcome to our world, right? So some of these building blocks are so sophisticated that you wish you had something parasitic happening to explain why your theory doesn't work, but it's just too perfect. I mean, if you have roughly speaking some building block which only connects through DNA hybridization, it's really hard to imagine that anything else is happening there. So there is no real van der Waals or electrostatic that seriously electrostatics is there, but which would seriously contribute would be an effect of comparable proportion with similar energy scales. So in that sense, these systems already have very specific interactions, in a sense more specific than interactions that are used originally in biology, like in with proteins, right? So proteins often have multiple way of binding, maybe not maybe undesired, so not a perfect key lock. These things normally are designed in. Again, it's rational design, right? So you can design it such a way that this parasitic effect are minimized. But yes, of course, this is common thing. If you have some non-specific interaction, of course it will hurt you. Even the thing.
But even in DNA nanoparticles, right? This exists, right? You typically anneal them, and I mean they're complicated preparations. They don't just snap into place, right?
That is true. That is, of course, true. One of my reasons why I sort of make this segue from this circular symmetric arrangement of spherical nanoparticle with DNA is because you can literally demonstrate how multicolored system of spheres with this central potential is extremely bad in designability. So there are so many errors that can come out of this. That's why this sort of directionality plus coloring was important. So once that thing is implemented, it becomes much more robust. I cannot say it's perfect, but it is much more robust. So that's why, I mean, this designer particle that I advocate so much.
I think there were multiple people. Michael, Tim? Tim?
I'll go first. Actually, a follow-up question to Sharon. So, I mean, we know very well how to talk about stability. We have free energy. I mean, when we talk about how easy to get something, we talk about nucleation barriers. But here is it difficulty that you have multiple nucleation barriers, that it's like a non-classical process?
It is.
And then how would you then quantify this? I mean, people also in protein folding, they're looking at transition rates. Is that
Yes. So when I explain sort of why we need to control nucleation, what the original motivation for this is the following. So if you just allow this to nucleate the way it does, it's not strictly speaking homogeneous, it's heterogeneous, but it can start from any point of your structure. What you will normally end up with half-built structure that then have trouble to merge together. So as a result, we concluded that the best way is to just decide which point will be our nucleation point, and you can bias the system to nucleate from there.
What I'm missing a bit is sort of the theoretical framework, because just like in free energy, we can write down actually equations.
Yes.
And I wonder also, I mean,
yes, you can. So I mean, again, think about this. So here you have local control, so you can literally lower the barrier, the nucleation barrier, at any point of your structure. So think about your structure as some lattice model, right? And you can decide where your nucleation will start. So because of this variability of interaction, so we literally design it so that, okay, we say this one will be our nucleation center, then the next ones will be strongly attracted to it, and then we design this whole thing as a sequence of generations. So what comes after what? So we literally design the pathway.
Final question from Tim, please.
Okay, I try to make it short. So I like your drawing here.
Thank you.
Depicting what's somewhat already exists, like aftermath, right? So these are DNA strands that bind to something, and they get mutated. Here the easy thing is that the selection is affinity, and you can pull it down. So the core of that is sort of, you have to find selection criteria where you can enrich whatever design you want to have in there. And that's what we have to think about.
Exactly. So for instance, you want your assembly to be triggered by a particular set of environments. So if then you expose your system to multiple sets and then say, oh, wait a moment, my success rate is this, so let's change something there. So yeah, something along those lines.
Thank you very much. Alexei?
Thank you.